So, this is a video about free and forced oscillations, resonance and damping. So, let's first consider some things that we've done already. You know that the period of a simple pendulum, 2 pi root L over G, where L is the length of the pendulum. You know the period of a mass on a spring, 2 pi root M over K. So you know that if you take a pendulum of length L and you set it in motion, you will get this period, whatever that is. If you take a spring of spring constant K, measure of the stiffness, with a mass M kilograms on it, and you set it in motion, this will be its period. So it will always, this pendulum on this planet will always oscillate at that period or with that period, and this mass on a spring will always oscillate with this period. Note, it doesn't matter what planet it's on, it will always have the same period, that mass on that spring. So if you set it in motion freely, free oscillations, then it will perform this kind of motion, where this is my amplitude and this is time, and of course that would be the period and that would be twice the period. So that would be a free oscillation, that is to say, no loss of energy. If you were to do it in air rather than a vacuum, this pendulum, this mass on a spring, then there would be some loss of energy, which would be shown by a loss of amplitude. So again, there's my time in seconds, and there's my amplitude in meters, and you can see the amplitude falling as time goes by. So there you have no damping there, and there you have light damping. Okay, so now we're looking at heavy, critical and over damping. So let's imagine we have a pendulum. Previously we had the pendulum in a vacuum and then we had the pendulum in air. Let's imagine we take the pendulum and we start our time at a maximum displacement at the amplitude. And so heavy damping would look like that, maybe. It takes a long time. Whereas critical damping is a quicker process, and over damping, here you might have your pendulum in golden syrup. So the amplitude is falling, that's not very good, but the amplitude is falling, but it's not falling to 0. So if we were to take this in a very real world context, if we were to consider this as the wheel on a car. So you have the wheel, and behind the wheel you have a suspension spring, and within that suspension spring you have what we call in the UK a shock absorber, what is more accurately called a damper actually. And if the damping is too heavy, then when your wheel comes off the road, it takes quite a long time to come back down onto the road, which isn't what you want. If you have critical damping, however, when the wheel comes down onto the road, it does that quickly and it stays on the road. With overdamping, you can imagine that your wheel just stays in the air. So this critical damping, and remember you have your period is 2 pi root m over k relationship. So you have to choose the stiffness, if you like, of this damper, which we call a shock absorber in this country. You have to choose the stiffness of this to get the damping just right, so that when your wheel hits a bump, it comes back down onto the road and stays there. If you think about light damping, then your wheel would be doing that. And clearly you don't want your wheel bouncing up and down off the road. This is what happens if your damper, your shock absorber, is no longer working. So what you have then is a mass on a spring, and it will just do this, and it is damped by air resistance, yes, but damped by energy being lost with that friction with the road. That's heavy damping, where it comes back onto the road but takes a long time. Critical damping comes back onto the road quickly. Maybe I should make my heavy damping rather a longer process. And the overdamping is where it falls, but it doesn't fall very quickly, and it isn't coming back onto the road at all.